So what we're gonna do here is all you need to take derivatives of trigonometric functions is to know that everything relates to sine and cosine. I didn't press, so I have to repeat all this stuff. So we go through this, all 6 trig functions. Tangent is sine over cosine, secant is 1 over cosine, cosecant is 1 over sine, cotangent. So all we need to know are the derivatives of sine and cosine, because then we can use the quotient rule to define the other 4 functions, the derivatives of them. So the rule of derivatives of trigonometric functions is all based on sine and cosine. Since the sine function deals with the y values and cosine deal with the x, on the unit circle, the horizontal axis is a cosine, the vertical axis is a sine. Going clockwise, those are the derivatives. The first derivative of sine is cosine, the first derivative of cosine is negative sine, and then the first derivative keeps on going. So with that, since we know the sine and cosine, find me the derivative of tangent. Right? We know that tangent is sine over cosine, so we use the quotient rule. The numerator is sine, the denominator is cosine. First derivative of sine is cosine. First derivative of cosine is negative sine. So since it's a quotient, we're doing a subtraction. So it's going to be cosine times cosine minus sine times negative sine over the denominator squared. So we have cosine times cosine is cosine squared. Negative times negative is positive. Sine times sine. Yeah, that's the identity. Theorem. It's an identity. It equals 1. So it's secant squared. That's the derivative of tangent. And the other ones would do the same way. Okay, let's look at some more examples. Let's go to example 1. We'll go to that sheet, and here we have the sheet. Find the derivatives of all 3 of these. Okay, A. Y is equal to x squared minus sine x. We could just do these by section. Derivative of x squared is 2x minus derivative of sine, and there you have it. Y equals e to the power x times sine x. We have to use the product rule. So fg f prime g prime e to the power x sine x. What's the derivative of e to the power x? E to the power x. Derivative of sine, cosine. Since it's multiplied, we add. So it's EX times sine plus EX times cosine. That's it, as far as we can go. I mean, we could factor out the EX and have sine plus cosine. We could do that, but we can't go any further. I know you'll spend most of your time trying to find, okay, there's got to be another way I can rewrite this using the trig identities. Sometimes it's just as straightforward as it is. Sine x over x. The top is sine, bottom is x. Derivative of sine is cosine. The derivative of x is 1. Since it's the quotient, we subtract. X times cosine minus sine times 1, all over the bottom square. And there you have it. And I do apologize because, I mean, to me, this is just straightforward using the unit circle and the fishy thing. So I apologize if I'm going too quick on this. If you want me to slow down, tell me to slow down. I will not be upset in any way, shape, manner, or form. Okay, ready? Yeah, so again, it's the fishy thing. If it's a quotient, it's subtraction. To subtract this minus this and square the bottom. The product rule, this plus this. All right, so let's look at now with the cosine function. Let's do these three. Example 2, let's do these three. Okay, the derivative of the first one. Derivative of 5e to the x. The derivative of cosine minus sine. So there's that derivative. Remember, just do the unit circle and you got it. And here we have the product. So we have sine. This is cosine. So derivative of sine is cosine. The derivative of cosine is negative sine. Cosine, cosine. Plus negative sine. There you have it. F is cosine. G is 1 minus sine. So derivative of cosine is negative sine. Derivative of 1 minus sine is negative cosine. Since it's a quotient, we subtract. 1 minus sine x times negative sine x minus cosine x times negative cosine x all over 1 minus sine x squared. Let's see what we can do in top. We have negative sine x plus sine squared x plus cosine squared x all over 1 minus sine x squared. Can we do anything on top?
Again, I just put one for the sine square plus cosine.
Yeah, so on top we have negative sine x plus 1. We can rewrite the top as 1 minus sine x. Just rewrite, just move them around. We have the same thing on top and bottom. So the first derivative is 1 over 1 minus sine x. Sine squared x plus cosine is 1. The commutativity, we can move them around, so it's going to be 1 minus sine, which is the same thing as the bottom. We have 2 of those, so we cancel one of them. Everybody good so far? Now let's do an application problem or a motion problem. Because remember, derivatives deal with motion. Example 3. A weight hanging from a spring, as below, is stretched down 5 units beyond its resting position and released at time equals 0. It bobs up and down. Its position at any time t is this position function, 5 cosine t. What is its velocity and acceleration at time t? So, how do we connect these? What's the amplitude of this spring? Yeah, amplitude is 5. What's the period? Yeah, because it's a cosine function, it's 2 pi. In other words, this thing's going to keep on bobbing up and down, plus minus 5. Show. What are its velocity and acceleration at any time t?
Cosine at cosine 0 equals 1.
Okay. So at 0, it equals 1. We have pi over 2, pi, 3 pi over 2, 2 pi. So let's draw the graph. But since its amplitude is 5, it's going to be 5. So down here will be negative 5. So what's it going to be at pi over 2? Cosine pi over 2 is 0. At pi, it's going to be negative 5. So that's what the graph's going to look like.
Oh, okay, yeah, 0, 5.
That's the graph. But what's the acceleration and velocity? We know the position of what you just did was there. That's what you just found. Velocity is the first derivative of your position.
That's the
Right. Exactly. Yes.
first
It's going to be
line.
negative 5 sine t. That's the velocity.
I can find sine and 0.
Let's friend functions, which is the second derivative of our position function. So the derivative of negative sine can be, yeah. So the derivative of sine is cosine. It stays negative. Nothing changes.
So why do we need to find the derivative of negative? Oh, and then acceleration is the second.
Is the derivative of velocity. So these are the answers at any time. This tells us how fast it moves up and down, and this tells us once we let go, how fast is it moving. Pretty straightforward.
Yeah.
We discussed this last class. So, okay, let's look at what's the jerk. What's the jerk associated with the last example? So we have all this information. What is the jerk? Little j as opposed to the large J for joule. The unit of heat displacement and movement. What is the jerk? The jerk is simply the derivative of the acceleration. The derivative of cosine is negative sine. Negative makes positive, so that's the jerk at any time t.
So we're just moving down basically different levels.
Right.
Of the
derivative. Both derivatives.
Yeah.
So this is the first derivative of our function. This is the second derivative of our initial function. This shoes. Because you asked earlier in the semester is can we take more than one derivative? Yeah. You can keep on in trig functions, since they're infinitely bounded by 1, -1, and negative infinity positive, you could take infinite number of derivatives. It's always going to be the same thing. It's going to be sine, cosine, right? But unit circle. Yeah, so, like I say, the circle never has a beginning or an end. Yeah, so they're derivatives. So that's examples 3 and 4.
So the jerk is the heat displacement.
No, joule. That's a unit of measurement. Oh, there, yeah. Because energy is all energy displaces heat. So example 5. We did this one already. Remember what the answer was? Again, we did that first example. And this was their example 5. You see how simple my was as opposed to what they were going to go through?
They were just going to lead us down a rabbit hole for
forever. Find the second derivative of the secant function. Exactly, yeah, it is for an entire class period. We did it all in less than 20 minutes. So let's find the second derivative of the secant function. And remember, secant is 1 over cosine. We don't run out of time. I know you guys can do this given time, but so first off, we have y equals secant x, which is 1 over cosine. So the first derivative, 1 cosine, first derivative of 1 is 0, is negative sine. And it's subtraction, since it's quotient. So we have cosine times 0 is 0, minus 1 times negative sine is negative sine, all over cosine squared x. So it's sine x times cosine squared x. How can we rewrite that? So we have sine x over cosine x times 1 over cosine. Right, so that's our first derivative. So now for our second derivative, we can start off from that one right there. We can start off from that one. Our f is sine x. G is cosine squared. So the first derivative of sine is cosine. First derivative of cosine squared, it's a power rule. Actually, this, what would it be? It's not gonna be 2 cosine. It'll be one step further. This leads into the next section. No, this is the chain rule, which again, using this method, we have to introduce it to you, which will make the next section much easier. What we have here is this. We have u to the power n. This is our function. The derivative of this function is n u n minus 1 du. So we take the derivative of the outside, leave the inside alone, take the derivative of the inside. So we took the derivative of the outside, leave the inside alone, times the derivative of the inside, which is negative sine. So it becomes negative 2 cosine sine. Because this is what the chain rule is all about. Take the derivative of the outside times the derivative of the inside. Take the derivative of the outside, which in other words, move the n down, subtract by 1, leave the bottom alone, times the derivative of the bottom, which is just u, du. So in this case, cosine squared, take the derivative of the outside, which is 2, bring it down, becomes 2 cosine, times the derivative of the base, which is cosine, which is negative sine.
Okay.
No, that's the chain rule. Yeah, and that's all the next section's about. So you see, they just threw it in there early. Well, actually, I threw it in there because I didn't want to do the derivatives of these individually. Because we could have done those individually and then combined them. Why?
Because that's what I was going to.
Well,
when I was still working on the second derivative, but I was about to just do that. So I mean, I didn't know changes.
we could have done this. You're right. It's would have been sine over cosine. So the derivative of this, and then the derivative of this would have been 1 over cosine. But this would be a lot easier since we're in sine and cosines. And I don't mind letting the cat out of the bag because we're going to do it eventually, so might as well do it now.
So then the derivative of secant would be, 1 over.
It'd be-
sine.
It would be 1/0 cosine negative sine. Yeah. It would have been sine over cosine squared,
Sine.
which gave us our tangent uh, secant. But again, that went back to tangent and everything. So here we'll do this with sine and cosine, and then put in those other terms later. So we have cosine times cosine squared, which is cosine cubed. Now, since we broke all of these down into their fractions, it's a subtraction. Sine times -2 cosine sine, so it's -2 cosine sine squared. And the denominator is g, so it's cosine squared squared. So we have cosine cubed plus 2 cosine sine squared over cosine to the 4th. If we took out the cosine, what would that give us? Okay, let's. Because now we have to put it back into terms of tangent and secant or cosecant, whatever we have left. So we have. I see what you're saying. Yeah, so if we take out 1 cosine, that means we can cancel one of the cosines. We have only cosine cubed on the bottom. Well, yeah, it was c cubed, but we took out a c here. Bottom? Oh, so yeah, it should be cubed. Yeah. I'm sorry. Yeah, good catch. So that's secant. So we have sine squared over cosine squared times 1 over cosine. Tangent squared x secant x. What's that? Yeah, but I'm thinking this one seems awfully small for the second derivative. Because this one is, you see, okay, look at the exponents. There's two there, there's one there. So we have a cubic function. Something tells me that this one should be a higher exponent. So let's see. So this is sine over cosine times 1 over cosine. So we have sine over cosine squared. Sine over cosine squared. So that gives us cosine cubed minus, would be plus 2 cosine sine squared over cosine to the fourth. On your cheat sheets, what is 1 plus 2 tangent? Not the derivatives, but look at the trig identities and the trig, or 1 plus 2 tangent squared.
One plus tangent square, yeah, is secant, right? Yeah. Okay. So then that means that you have two secant squared. Oh, no.
Mm-mm.
I think that's-
Okay, so we have cosine cubed plus 2 cosine squared, cosine sine squared over that. That's 1 over cosine, 2 over cosine cubed. I'm missing some exponents there. Okay, hold it for this one then. Let me look at another way of doing this one. Tangent secant. So the derivative of a tangent cosine. So it's going to be cosine squared plus sine squared. So it's going to be secant squared. And derivative of secant is 1 over cosine. So it's 1, 0, cosine negative sine. Sine over cosine squared. which is tangent secant. So it's secant. This is a product rule. So we have secant cubed plus tangent squared x secant. That makes more sense. So there it is. If we break it down to sine and cosine, that makes it more difficult. So if we just take tangent and secant and just take the derivative of those individually, tangent is sine over cosine. The derivative of that is secant squared. Secant, the derivative of that is tangent secant. Since it's the product rule, we add them and then we have it.
I just asked ChatGPT what it was, it gave it the same thing.
Well, see, and that's just, I don't want you to ask it what it is. I want you to ask it, how did you get it? It's the why that's important. That's why, that's what, when we start talking about AI in learning, don't make it do the work for you, because you don't know if it's right or wrong. But ask it, okay, why did you get this? How did you get that answer?
Right.
And that's so your next prompt is,
How did you get it?
yeah, from the standpoint of a student, how did you get the previous response? And
I think with, I mean, I think, yeah, with ChatGPT, I think you can actually have it, the like custom interactions on there. So you can set it to respond in a certain manner.
well, you can tell it on the prompt. You can give it as a professor, as a student, as a beginner student. How did you get that answer? And it will modify its answer. It should modify the answer, but remember, it's generative response. That means it's basing its response on what it's learned from the past.
Right.
So you're basically asking a junior high kid who just learned it.
Yeah.
So yeah, that's the answer for that derivative. So that's our second derivative, actually. Because our first derivative was sine over cosine squared, which gave us tangent secant. The derivative of tangent secant is secant cubed x plus tangent squared x secant x. That's what we just found there. See, it should work both ways. Tangent is sine over cosine, secant is 1 over cosine. We should be able to get the same answer using that. But it didn't. Stupid computer. So there's that and that.
So, why didn't it work?
I don't know, that's what I have to look at, is because the algebraic manipulations of it. I did something wrong, so I have to go back and look at each of the steps.
Okay. So it was just something within the steps.
Yeah, because ideally, whether you break it down into simplest forms or leave it as a tangent secant, it should get the same answer because they both come from the same place. Now, because our functions are differentiable on the entire domain, from negative infinity to positive infinity, that means it's continuous at every point, which means that we should be able to take a limit point at any point along the way on the trig functions. So that means if we take a limit point, we can just go with direct substitution. Just remember our first thing, unless you get 0 over 0, if you get an answer, it's good. If you get 0 over 0, that means you can algebraically manipulate it. If you get anything else, the answer doesn't exist. So we set x equal to 0. 2 plus secant at 0 over the cosine of tangent at 0 secant at 0 is sine 0 over cosine 0, which is 0 over 1, which is 0. So square root of 2 plus 0. Tangent at 0 I'm sorry, secant at 0 is 1 over cosine, so it's 1 over 1. It should be 1, not 0. Tangent at 0 is 0. So we get square root of 3 over cosine of pi. Cosine at pi is -1, so we get negative radical 3 is our answer. So far, so good. Just direct substitution. Plug in 0 in all those places. Secant is 1 over cosine. Cosine at 0 is 1, so we get 1 over 1, so that's 1. Tangent is sine at 0 over cosine at 0. Sine at 0 is 0 over 1, so that's 0. And just plug them in. There you have it. All right, so that does it for section 5. Now let's look at section 6. It should go pretty quick because it's going to be the same type of thing. Chapter 3, section 6. The chain rule. This is day 16. Day 16 means we're exactly halfway finished with the semester. We have 8 more weeks left. So the chain rule, basically it looks like this. So let me give you an example sheet here. I'll show you 2 examples. Remember what we said earlier, that u to the power n. The derivative is n u n minus 1 times the derivative of u. So here we have this example. So the derivative, this is our n. So we bring it down, leave the base alone. We have 2 minus 1 here. Times the derivative of the inside. The derivative of 3x squared plus 1 is 6x. If u equals 3x squared plus 1, then du is 6x. So we have 12x, 3x squared plus 1. There's our derivative. So basically, the chain rule simply tells us that we can have the product and quotient rule inside the product and quotient rule. That's all it tells us. We just keep on going on how many times we have it. Let's look at example 2. A moving object along the x-axis, so its position at any time t is given by the function x of t is equal to cosine t squared plus 1. Find the velocity of the object. Remember, this is our s. This is our position function. It's moving horizontally. How do we find the velocity? First derivative. So we need to find the derivative of x with respect to t. Remember, what you have to do is define u. U is the internal function. In this example, what is our u? T squared plus 1. This is our u. So du will be 2t. What we have here is cosine u. So the derivative of cosine u is the derivative of cosine, which is negative sine, times du. So it's negative sine of t squared plus 1 times 2t. So this is how you'd write your answer. We can go again. We can take another derivative if you want. We can find the acceleration. We do the same process. But for the sine function, we have to do the chain rule there. Actually, let's go ahead and find that. This is the velocity, which is the first derivative of our position. This is our acceleration, which is the second derivative of our position. So we want to find the second derivative with respect to t. That's f, and that's g. We're going to use the product rule. Negative 2t sine t squared plus 1. So the first derivative of negative 2t is negative 2. And the first derivative of sine t squared plus 1, remember, this is sine u. So the derivative of sine, the derivative of sine is cosine t squared plus 1 times the derivative of the inside, which is 2t. Do the fishy thingy, it's plus since it's a product. So we have negative 2 sine t squared plus 1 plus negative 2t times 2t cosine t squared plus 1. And just fix it up. Positive times negative is negative. 2 times 2 is 4. T times t is t squared. And there's your answer. That's the acceleration function. And that's the worst thing about a chain rule of trig functions. It'll keep on growing. There we got it. All right. Let's look at the next example. Example 3. Differentiates. Again, we use these trig functions because we know they're differentiable throughout the entire domain. Differentiate the sine of x squared plus e to the power x with respect to x. So what we have here is sine of u. The function within a function, composites. So what is du going to be? Two x plus e to the x. So the derivative, so we take the derivative of the outside, which is sine. What's the derivative of sine? Cosine u times du. So cosine of x squared plus ex times the derivative, which was 2x plus e to the x. And that's it. You could write it 2x plus e to the x times cosine x squared plus e to the x. That's our derivative. But to make it easier, you have to be able to locate what the u is. The u has to be the innermost function. Because you take the derivative of the outside, leave the inside alone, then take the derivative of the inside and just multiply them. Differentiate e to the power cosine x. And I put this in there because these are important rules. This is what we've been talking about. The derivative of e to the power u is eu du. So just write the equation down and take the derivative of the inside of the exponent. That's all it tells you. Leave this one alone, the derivative of the exponent. So knowing that, our derivative, since it equals e to the cosine x, our derivative will be what? E to the cosine x times, what's the derivative of cosine x? Negative sine x. So it's negative sine x e to the power cosine x. There's our derivative. And there's really no end to the number of times you could have a function within a function. I mean, on a final exam, I could give you something like this. Where the answer would be this times the derivative of that, which would be a product rule. Would be long, but that's you see what this is trying to tell us. EU du. Leave this alone and just pretty much take the derivative of the exponent and multiply it. That's why I love e, the function e in calculus. It's always going to be there. You just take it's just the exponent. Number 5. Find the derivative of g of t equals tangent 5 minus sine 2t. Okay, let's right. So the first thing we have to do, this is going to require a couple. Let me get the door. So we have here is g of t equals tangent u. So u is equal to 5 minus sine 2t. So du is, we have to take the rule of this one. So this one is also a sine of u. So the derivative of sine is cosine times the derivative of 2t, which is 2. So that is what our du is.
Because when you're taking it, you have to find, so when you're doing that, you also consider 2t to be the u of sine.
Well, because u is a function of t. U is a function of t, because that's the only variable inside there. So the derivative of tangent is what? It's secant squared times du. So it's secant of 5 minus sine 2t times negative 2 cosine 2t. Which is negative 2 cosine 2t times sine squared 5 minus sine 2t. There's your answer. All I did is I put this in front because I don't like it back here because it seems like it's an extension of sine. Keep on going. Oh, I'm sorry, secant. Yeah, secant. Secant. Secant squared. So basically, this is really what it tells you. So tangent of u equals secant squared of u times du. Once you define what u is, find du, plug and play. Ready? More? Let's do some more. The power chain rule. I'm missing some sheets. So let's do all of these. How would I do it? How do you think I would do
But, so you have 7 in front of the 5x cubed minus x to the power of 4 to the power of 6.
it? Yeah, so basically what you have here is u to the 7th times du. Right. So you're right. Our derivative would be 7 5x cubed minus x to the 4th to the 6th times
5x cubed minus
15x squared minus. Because again, it's much easier if we look at it with respect to the u. Because then we have 7u to the 6th times du. U is equal to the 5x cubed minus x to the 4th. Du is 15x squared minus 4x cubed. Plug that in for that, plug that in for that, and you're done. B, the derivative of 1 over 3x minus 2. Now, again, how does this relate to what we're trying to do here? We can rewrite our function like that. So now our u is 3x minus 2 and du is 3. We have u to the power negative 1. Take the derivative of that. Negative 1 u to the power negative 2 du. This looks a lot easier than all this. So the way this is written is negative du over u squared. Du is 3x minus 2 squared, and there's our derivative. So far, so good. Let's look at C. Oh, there's example 6C. The derivative with respect to x of sine to the 5th x. Basically, what this one is u to the 5th. du. What is u? Sine x. And so du would be cosine x. Five sine to the fourth x times du, which would be cosine x. And there's your derivative. E to the power radical 3x plus 1. I have others. Yes. Because that's the u. So the derivative of sine to the fifth is 5 sine to the fourth times the derivative of sine, which is cosine.
Maybe you use it as use sin x for you. I don't get that part.
What's that?
You know, you use your sin x. right?
My u is sine x.
Yeah, so
Because x belongs to the sine function. You can't just have, u cannot be sine. It has to be a sine with respect to your argument, which is u. Am I taping this still? Yes. So what I have here is that.
um,
That's pretty much what I have. Okay, so do the E one. And the easy E one should be pretty straightforward for us. What should I have? I'm missing a page. I'm missing a page. Oh well. Remember the rule we had? EU du.
U is going to be 3x plus 1.
Which is 3x plus 1 to the power 1/2. Now our du is going to be the power comes down 1/2. Subtract 1, which is negative 1/2, times the derivative of the inside, which is 3. So my du is that. So the derivative is EU du, which is e to the radical 3x plus 1 times 3/2 radical 3x plus 1. Which I can make it look easier. Not easier, but more clean. And there's my derivative. Even though they say you're not supposed to have a radical on the bottom, we're not gonna waste our time with that. What do y'all think? Plausible, doable? Once you localize what the U is and take a DU, it's EUDU or UDU.
Is E the only, I can't remember.
That stays the same,
It's
which is why I like it so much.
Yeah.
This one I like. Gotta find the other sheets. Anyway, we'll just do 8 then. In example 4 in section 3.2, we saw the absolute value function, y equals absolute value of x, is not differentiable at 0. Why not? Why is it not differentiable at 0? Even though the function is differentiable on all other real numbers. Because it fails the limit test for limit left, limit right. If it doesn't approach, we have negative slope on one side, positive on the other side, so they're approaching different values. So that's why he's saying that. So in this kind of example, if we can rewrite the function, if we can rewrite absolute value of x as that function, because all it really does is change the value of the function to be a positive value, we can define it as that. Let's take the derivative of this.
So that would be X squared, the power.
So it would be u to the power 1/2.
So U equals,
U is equal to x squared, so du is 2x. So what's the derivative going to be? So our question right now looks like this: e to the power 1/2, u to the power 1/2. Since it's a power function, we have to bring that down and subtract 1 times du. Which is du over 2 square root of u. Now all we have to do is just plug numbers in. What is du? 2x. What is u? X squared. So the 2's cancel. I'm missing that last sheet. Is that last sheet? I'm missing one more example after this. So what's the answer? What is square root of x squared? No. Because we're taking the derivative of the absolute value. Where x cannot equal 0. I know, at first I thought, okay, no, we only have one. We're not supposed to have one. We're doing absolute value. So that's the reason. So if it says if it's not differentiable at a certain point, but it's a continuous function, rewrite the function. And this will be our last one since I can't find the last one. Find the slope of every line tangent to the curve at this point. I'll show that the slope is positive for every point. Show that the slope of every line tangent to the curve, this curve, is positive.
So we want to show that the derivative of that function.
Is going to be
always
positive. Right.
Perfect.
Yes. Now, if we were Fred Flintstone or Barney Rubble, we would use the quotient rule. But we're not going to use quotient rule. What are we going to use? Chain rule. How are we going to use the chain rule with this?
We know that u is 1 minus 2x.
Yeah, because we have to rewrite that because now it's quotient. Now we could use the chain rule.
So 1 minus 2x is u.
Which means dx, du would be what? -2. So what's the derivative? Right now we have u to the power -3. The derivative will be -3 u to the -4 times du. -3 u to the 4th du, which is the same thing as -3 du over u to the 4th. What is du? -2. 1 minus 2x to the 4th. Negative is positive, 6 over 1 minus 2x to the 4th. So why will all of our slopes be positive? Why will all of our slopes be positive?
He is given even exponent.
Yep.
And then a positive number.
It can never be negative because the top's positive. Even exponent will make, even if this is negative, makes it positive. So that's why.
In other words, the function's
Exactly. Yes, it's an even function. It's symmetric with the y-axis. That's it. I can't find the last one. I packed it in somewhere else. I can't find it. So that finishes up sections 5 and 6 of chapter 3.
I wasn't too bad. The chain, I thought the chain rule would be harder than that, but.
It's not, once you see it, once it clicks, it saves you so much time, because now we don't have to go through the quotient rule anymore, really. This makes it a little much easier, because a lot of times the product rule is much faster.
Yeah, I mean, the quotient rule is, it's like a dinosaur.
Well, so it's dinosaurs, limits, and epsilon delta stuff is this.